Good morning everyone. I'm Yi Liao, and today I will present a study titled Microstructure and Properties of WC-12Co fabricated by laser powder bed fusion using plasma spheroidized powder. In this research, the authors compared WC-Co samples printed by LPBF using two kinds of powder. One is the traditional granulated powder, and the other is plasma spheroidized WC-12Co powder made by a 100 kW radiofrequency plasma system. The goal was to see how plasma spheroidization improves densification, microstructure, and mechanical properties. In other words, the study aims to evaluate the printability and performance of WC-12Co powder after plasma treatment. The experiments were designed under identical LPBF parameters. A laser power of 320 watts, scanning speed of 450 mm per second. A hatch spacing of 100 micrometers, and a layer thickness of 50 micrometers. Both powders were fabricated under the same conditions so that differences could be directly attributed to the powder characteristics, such as particle shape, density, and laser absorptivity. After fabrication, the samples were analyzed using SEM, EDS, EBSD, and XRD for microstructure and phase identification. Mechanical tests included Vickers hardness and were testing using a ball-on-plate tribometer. All results were then compared between the plasma spheroidized sample, called sample S, and the granulated powder sample, sample G. The plasma spheroidized powder showed a much smoother surface, denser internal structure, and higher laser absorptivity. Because of that, the porosity in the printed sample was reduced from 12.4% to only 2.9%. A 76% improvement in densification. The smoother particles also allowed better cobalt flow during melting, which filled potential keyholes and reduced cracks. So overall, plasma spheroidization strongly enhanced the density and uniformity of LPBF-built WC-Co. Hardness testing showed that sample S had a higher Vickers hardness value due to its finer and more evenly distributed WC grains. During wear tests, the coefficient of friction of sample S was lower, and its worn surface was smoother. The wear mechanism also changed. Sample G mainly suffered from abrasive wear, while sample S showed a combination of abrasive and adhesive wear, which indicates more stable frictional behavior. This means the plasma-treated powder not only improved density but also enhanced wear resistance. In summary, plasma spheroidized WC-Co powder shows higher laser absorptivity, smoother particles, and better flowability. Porosity was reduced by 76%, leading to higher densification. The appearance of alpha-Co phase improved both hardness and wear resistance. Therefore, plasma spheroidization is a very promising technique for producing high-performance WC-Co parts by LPBF. Thank you for your attention.